exactly what this angular momentum conserving upper level zonal winds look like if we assume, I think this was a forcing maximum at 8 degrees latitude, where the dividing boundary between the southern and the northern cell is located at 20 degrees latitude. Again, notice that the winds are exactly zero at plus or minus 20. This is what we call phi 1. And then in between this latitude, within these two latitudes, we develop easterly flow. And notice how this distribution is still symmetric about the equator, with a minimum at the equator. Now, in these simple models, again, we assume that we know the upper level winds. These are constrained by conservation of angular momentum. And so now we can infer what the temperatures in the, again, upper branches, in the upper troposphere need to look like to be in thermal wind balance with the distribution of the winds. And this is what is shown here. The open dots represent the forcing that is imposed in this model. Again, notice how this maximizes at about 8 degrees. Much larger than the one contained in the northern cell. You basically don't even see it. So this models really allow us to understand why, again, in a solstitial pattern, the pattern of the Hadley cell is dominated by one single broad, very strong cell. There were other features that were described by Lindzen and Howe in terms of what we would see through the course of the seasonal cycle of the zonally average Hadley cell that in fact do not necessarily correspond to what we see in the observations, but I don't have time to cover that. But again, let me here emphasize that when we think about monsoonal circulations as cross-equatorial Hadley cells that approach conservation of angular momentum, Lindzen and Howe thus provide one first-order picture and theoretical framework to interpret some features of these circulations. But I want here to emphasize the connection with the moist convection and rainfall patterns, because both Held and Howe and Lindzen and Howe were completely based on dry theory. We do not consider the presence of moist convection. And so how should we think about now the interaction between this large scale of returning circulation and where convection would develop and where precipitation maxima would develop? And this is where we use the convective quasi-equilibrium view of monsoons that was hinted at by both Adrian and Spencer yesterday. And so when we think about what convection does and how it interacts with the large-scale circulations, we really have shifted from ideas that interpreted the latent heat release associated with convection as the driver for large-scale circulation to this more statistical view where, in reality, convection consumes the instability cape that exists in the vertical column on a much faster scale than the scales that are associated with the buildup of CAPE. So convection is a fast process relative to large-scale advection or radiation. Convection acts on a scale of about 2 to 3 hours. All these other processes that lead to the buildup of CAPE act much more slowly. Radiation, we have in mind typical time scales of about 10 to 20 days. And so convection is rapidly consuming that stability, so much so that in fact there is no energy that is available to drive this large-scale circulation. So what we really should think about, when we really think about what convection does and how it interacts with the large-scale circulation, we should think about it as a fast process that basically constrains the temperature profile in the free troposphere to be the ones that follow a moist adiabat. And of course, that moist adiabat, to which the temperatures relax, are set up by the moist energy content. Let's think about moist static energy that we introduced yesterday in the boundary layer of convective regions. And I'll go back to the slides. Let me show you here a schematic that I borrowed from Bill Booth. So again, how should we think about this convective quasi-equilibrium idea and what they tell us about the thermal structure of the free troposphere? Again, let's suppose that we are in a situation where convection is not happening. And for whatever reasons, for instance, increase of evaporation over the ocean, the moist static energy in the boundary layer increases. In this region, then, of course, instability develops and convection very rapidly develops, so that increase of moist static energy in the boundary layer is spread out through convection in the vertical column. Of course, now, because of the processes that we discussed yesterday, the temperature profile is the one set up by a moist adiabat, a parcel going up, trying to conserve its equivalent potential temperature. And so convection does heat up the free troposphere. If convection did not alter the moist static energy content in the boundary layer, we would see that the two would be completely aligned. But of course, as we learned yesterday, convection does impact the moist static energy content in the boundary layer by cooling it through evaporation of rainfall that falls in the boundary layer. But at the end of this very fast process, we have that variations in the upper tropospheric temperature are in equilibrium with changes in the boundary layer moist static energy constant, so that, again, the two are in equilibrium. And so this framework does allow us to establish a link between variations in the subcloud or boundary layer moist static energy and the free tropospheric temperature. So now, if we put these things together and we use this, let me go back here, and we use these ideas of how upper tropospheric temperature variations are linked to variations in the moist static energy in the boundary layer, the fact that because of conservation of angular momentum, that of course acts irrespective of the presence of moisture and moist convection or not, we know that upper tropospheric temperature maximized close to the polar boundary, actually where the polar boundary of the circulation is located, then we can invoke the fact that this upper tropospheric maxima in a moist convective atmosphere will be coupled to maxima in the distribution of the moist static energy, and therefore we can again use this correspondence, this covariation between upper tropospheric maxima and boundary layer moist static energy to predict that the boundary of the cross-equatorial Hadley circulation would coincide with maximum in the boundary layer moist static energy. As I mentioned, in this view, we do not expect precipitation to maximize right at the polar boundary of the circulation, but it maximizes slightly equatorward. And what might ask, why is that the case? And that is because, of course, precipitation is not only linked to the availability of moisture, but of course, it's also connected to where ascending motion occurs. And if you think about a much stronger cross-equatorial Hadley cell relative to the summer cell, again, the packing of the streamlines, which is basically a measure of the strength of the vertical motion, will be much higher here on the equatorward side of the polar boundary of the circulation. That is to say that most of the vertical motion is occurring equatorward of the poleward extent of the circulation. This is where precipitation maximizes. Okay, really here I summarized in, what was it, a discussion of 5 to 10 minutes, work that has been done basically through 20 years. I hope that, again, it was clear. But here the thing that I want to emphasize is that we have theories that allow us to link important aspects of this cross-equatorial cells to the distribution of moist static energy in the boundary layer. In particular, we expect that development of that, again, the establishment of cross-equatorial Hadley circulations will be associated with the development of a subtropical maximum in moist static energy. And here I will try to convince you that in reality, that maximum, even in the observations, is really not associated with the development of temperature maxima, but moisture plays a very important role. So let me emphasize how problems in the interpretation of monsoons as sea breeze circulations is something that we as a community have been aware of for 100 years now. And here I'm quoting a paragraph from Simpson, 1921. I'm going to read it out loud to you. It has generally been held that the southwest monsoon, this would be the Indian monsoon, owes its origin to the great difference of temperature which exists during the summer months between the heated land surface of India and the surrounding oceans. This theory has to face the difficulties that the temperature over India is much higher in May before the monsoon sets in than it is during the monsoon itself. That the temperature is higher in years of bad monsoon than in years of good monsoon, and that the part of India which has the highest temperature and the lowest pressure is a region of practically no rainfall throughout the monsoon. Let me emphasize how maybe what has really changed, even if we have been aware of this for the past 100 years, maybe an alternative framework based on fundamental theories has emerged only in the past 20 years. Okay, but I want to provide some observational evidence that in fact we do see this covariation between maxima in moist static energy in the boundary layer, upper tropospheric temperature, and precipitation. And this is work that has been done, not by myself, by other scientists, Bill Booz among others. And so this is a plot based on a reanalysis product. I forget which one. I think it was probably ERA interim, or maybe even ERA 40 at the time, looking at the distribution of moist static energy in shadings. Here, it's in units of temperature. You just divide by CP and you get units of temperature. The line contours represent mid to upper troposphere temperature. And here the white line basically represents the contour within which monsoonal precipitation develops. And this is for the different monsoon systems: South Asia, Northern Africa, North America, Australia, Southern Africa, and South America. And I hope that you can see that in general, this co-variation, this co-location between the boundary layer moist static energy and upper tropospheric temperature, and how this, again, moist static energy tends to maximize a little bit poleward than the monsoonal precipitation, is seen with some, of course, variability in patterns in all monsoon regions except the North American monsoon, where in fact you see that upper tropospheric temperature, again, are a little bit, tend to maximize, again, in the regions that are different from where the moist static energy in the boundary layer maximizes. So again, this points out to the fact that the North American monsoon is a bit different than the other monsoon systems. Of course, and I'm not sure I'll have time to go back to this point again, so let me say it right now. Of course, one might think, oh, but of course, moist static energy in the boundary layer seems to have is much more structured than the upper tropospheric temperature. And absolutely, yes, you are right, because the upper tropospheric temperature in the tropics is constrained to have weak gradients. This is something that has been hinted at yesterday as well. The upper the tropical atmosphere, because rotation is dynamically not important, cannot sustain strong temperature gradients. And so whenever you have that, for instance, where convection happens, you have that, of course, the atmosphere is being heated up in this region, relaxing temperatures to a moist adiabat. That temperature anomaly spread out remotely through fast gravity waves. And we have learned a lot about, for instance, even about the influence that topography might have on monsoonal circulations by looking at processes that control the distribution of boundary layer moist static energy. Again, I'll try to return to this a little bit later if time allows. But let me show you how, again, I really want to emphasize how if we really were to believe that the near surface temperature gradient is a driver, an external driver of monsoonal circulations, this would lead us to wrong predictions. And this is from a paper that we wrote with one former student of mine, Jennifer Walker, where we looked at interannual variability of the Indian monsoon. There we introduced a index for the year-to-year variability of the monsoonal circulation and associated precipitation patterns by looking at the moisture flux converging in a broad region here. Doesn't matter. Let's just say that we have an index that allows us to distinguish a wet from a dry monsoon region. This is the climatology of the near surface temperature. And this is the regression of the temperature in the near surface on our monsoon index. You can interpret this as the anomaly in temperature during a wet monsoon year, a year where it rains a lot, one standard deviation. Monsoon stronger by one standard deviation. And so you see that a year with a strong monsoon is characterized by weaker temperature over land and larger temperatures over the ocean. So if we now take a zonal mean in this sector, this is what those meridional temperature gradients would look like. The blue, strong monsoon year, the red, weak monsoon year. Again, there is no evidence that a strong monsoon year is associated with a stronger meridional temperature gradient. In fact, it's the opposite. And one might say, well, but we all know that this is a coupled system. So once it starts raining, you get evaporation from the surface, cloud masking the insolation. And yet, if we look at the spring before, the spring preceding a strong monsoon year, we still do not see any evidence of a stronger meridional temperature gradients. If I were to show you the moist static energy gradient, we will clearly see a much stronger moist static energy gradient in year of a strong monsoon. And so let me here emphasize how strong monsoon years are characterized by a weaker near surface meridional temperature gradient. So any index built on the near surface meridional temperature gradient is giving us the opposite answer. Okay? Okay, but this is also true on intraseasonal time scales. Again, here I'm going to go super quickly. This is an index for the onset of the monsoon that we introduced in Walker and Bordoni that might be the topic of a hands-on on Thursday. So we'll go through that more in detail. I'll talk a little bit more about it tomorrow as well. But let me just emphasize that once we have an index that tells us a time of monsoon onset every year, then we can start building composites of how thermodynamic and dynamic variables change at the onset of the monsoon. And this is for the upper tropospheric temperature. Again, these are the patterns of how temperature change in an Moeller diagram, latitude versus time. Again, this establishment of a monsoon is accompanied by this development of the upper tropospheric maximum, located more or less in the upper troposphere, in the subtropics. And again, notice how this is preceded by the buildup of this large maxima in equivalent potential temperature in the boundary layer. But here, what I really want to show you is, again, how this maxima in moist static energy or equivalent potential temperature, or these variables are strongly connected to one another, are driven by moisture. They are not driven by temperature. So this is the composite at day 0 over all of the years that we looked at of equivalent potential temperature or moist static energy. Again, you can think of this as moist static energy if it's simpler for you. And this is the distribution of the temperature in the boundary layer. So we clearly see that at the time of monsoon onset, temperature is larger over land than it is over the ocean. So if we now look at how these patterns, moist static energy and temperature change 15 days after monsoon onset relative to the time of monsoon onset, we clearly see that the onset of the monsoon is associated with a large positive anomaly in moist static energy over the continent. But this is not driven by a large positive anomaly on temperature. After monsoon onset, temperatures decrease over the continent. And so the fact that we have this enhancement in the gradient of moist static energy is all driven by moisture, not temperature. Again, this is to say that if we were to develop an index based on the strength of the monsoon on intraseasonal time scale based on near surface temperature gradient, this would not give us the right answer. Okay, but then the question is, okay, so we cannot think about monsoons as the sea breeze circulations. We should think of them as cross-equatorial or returning circulation, but then the question, again, let me maybe go back to a map of precipitation for July. Again, but then the question is, why do convergence zones remain closer to the equator? And so things remain more equinoctial in terms of the associated returning circulation over the ocean than they do over land. There must be something about land that allows for much more pronounced migrations of the ascending branches of these regional Hadley cells and associated convergence. And so there still must be a role for the land or the land-sea contrast. And so we tried to explore a little bit what that role might be with Tapio Schneider, my former postdoc advisor at this point, many years ago, 2008, 2007 starting. And so we took an atmospheric GCM, idealized in many ways, but here the important idealization that I want to emphasize is that basically we got rid of all of the land-sea contrast, and we basically used as a lower boundary just a slab of ocean of a given fixed mixed layer depth. This is something that we can prescribe in the model. And so we imposed a seasonal cycle of insolation, and we looked at what are the patterns of seasonal changes in the precipitation and circulation patterns. And this is what we got for, again, this is the observations over the Indian monsoon region. We saw a little bit of a different version of this of Muller diagram that I already commented on, where the rapid onset of the monsoon appears as a migration of the main convergence zones at subtropical latitudes. And so instead, these two bottom panels represent two different simulations that we performed on this Aquaplanet model. The center panel shows the simulation where we make that slab of ocean very shallow, just 0.5 meter of water. Whereas the bottom one shows the simulation where we make the mixed layer much deeper, 50 meters. Let me emphasize how 50 meters, so a few tens of meters, is the typical depth of the mixed layer over the ocean. So this simulation here, those results I'm showing in the center panel, 0.5 meter of water, is not trying to represent what the ocean is doing on any region in our planet. It just wants to basically to simulate monsoon-like transitions in the tropical precipitation patterns and associated overturning circulation in an Earth-like planet without any land-sea contrast, but where the lower boundary is just a swamp. That is to say, a lower boundary whose heat capacity is small enough to be comparable to what we see over land-covered regions on our planet, but where, of course, we have infinite supply of moisture. So this is, again, trying to represent the heat capacity conditions that we see over land regions in our planet. Again, let me emphasize how, of course, this is not realistic in terms of moisture availability over land, which we know is, of course, limited. Okay? And so then we, through these simulations, we argued that you do not land-sea contrast to simulate monsoon-like transitions in the precipitation patterns, but you just need a lower boundary that has a very small thermal inertia. And again, we argued that these patterns that we simulate in this over this warm surface are monsoon-like in the sense that we see that precipitation is primarily organized along subtropical convergence zones that shift rapidly from one summer to the opposite summer hemisphere. If you were to live on this one like planet at 20 degrees latitude, for instance, north of the equator, you would really experience this rapid shift from very, very dry winters to much wetter summers. If we look at the simulation with a much deeper mixed layer, we see that things don't have a very muted seasonality in terms of precipitation patterns, both in terms of location and magnitude of precipitation there. I know that if you are not used to think about aquaplanets, it might not be very easy to think about what this might look like. And so here I'm showing a snapshot from this shallow mixed layer simulation during Northern Hemisphere summer, where again, shadings represent precipitation and the vectors represent the lower level winds shown against the observations for the month of July, focusing over the Southeast Asian monsoon sector. And I hope that you can see that during Northern Hemisphere summer, even in the absence of a continent in the subtropics, we see that the rainfall band migrates at latitudes in the subtropics that are similar to what we see over the Southeast Asian monsoon, with the establishment of a southwesterly close equatorial flow that again is similar to what's seen in the observations. And let me emphasize how the fact that we can simulate monsoon-like transitions in the tropical precipitation and circulation patterns, even without lengthy contrast, but over a shallow mixed layer, is pointing to the importance of land to support the development of monsoons, not through the fact that it helps establish these near surface temperature gradients, but because it has a small enough heat capacity that it can allow for more rapid changes in the low level moist static energy content, therefore allowing for the establishment of more cross-equatorial Hadley circulations. I haven't really showed you yet what the overturning circulation looks like. For instance, at times where the subtropical where the rainfall band is located in the subtropics, and this is exactly what we see. We see that the migration of the rainfall maximum in the Northern Hemisphere subtropics is associated with the development of a cross-equatorial Hadley circulation. And I hope that you can see in the cyan line the wind patterns. Those are the zonal winds, upper level easterlies that we found almost throughout the monsoon region, flanked by a stronger subtropical westerly jet in the winter hemisphere, a weaker westerly jet in the northern hemisphere, and with the establishment of westerly flow close to the surface. And notice how the polar boundary of this circulation, while coincides with the subtropical maximum in the moist static energy in the boundary layer shown by this red line, just equatorward of which maximum precipitation is found. Again, this is very much in agreement with the theoretical expectations built on much simpler models. Again, if we look at the distribution of the moist static energy in the boundary layer, we clearly see the establishment of this reversed gradient. Again, moist static energy increases up to a subtropical maximum as we move away from the equator. We are over an aquaplanet, and what this means is that temperature and moisture go hand in hand. So in this case, again, because we are over an aquaplanet where we're not limited in terms of moisture supply from the surface, this reversed gradient in the moist static energy patterns, of course, coincides to a reverse gradient in the temperature patterns. And again, let me emphasize how we can build this reverse meridional temperature gradient, again, considered one of the hallmarks of the development of the Indian monsoon, even without any subtropical landmass, let alone topography. After this work, I can say that exactly the idea of studying monsoons has really picked up wildly in the literature, but there have been quite a few follow-up studies looking at different aspects of again, simulated monsoon-like transitions over an aquaplanet. And here I want to cite work by Ruth Geen, where she performed many aquaplanet simulations, changing different aspects of the planetary configuration. For instance, they were not this rotation, but the rotation period around the sun. So the length of the seasonal cycle, the depth of the mixed layer. And here I'm just showing results where she basically, you can interpret this as changing the depth of the mixed layer. And so here, what we are looking are, each line represents a different simulation. And here we're looking at the ITCZ migration rate. So this is the rate at which the ITCZ shifts as a function of the position of the ITCZ. And so for simulations in which things remain more or less close to the equator, you clearly see that this paths represent circles. Notice how, for instance, in the very shallow mixed layer, and this is what the thick line, black line represents, we clearly see an ellipse shape, and we also see that the ITCZ migration rate reaches a peak. So this is where the ITCZ is moving more rapidly away from the equator as we go into the summer hemisphere, as the position of the ITCZ is able to become further away from the equator at a critical latitude of about 7 to 8 degrees. This is to say that if your lower boundary has a heat capacity that is small enough for the ITCZ to migrate past this critical latitude, the ITCZ does not want to stay there. The ITCZ that rapidly jumps away from the equator. And this rapid jump away from the equator was something that was already pointed out by Linzen and Howe. He really emphasized how, as you move the forcing latitude away from the equator, the separation between the poleward boundary of the circulation and this latitude of the maximum forcing increases. And that is because of nonlinear properties, of the circulation. The circulation becomes more angular momentum conserving. And also the advection of moist static energy by the lower branch of the circulation also plays a role, because it helps advect lower level moist static energy close to the equator further poleward, therefore pushing the subtropical maximum in low-level moist static energy. So again, that is to say that we really need this lower boundary to have a small enough heat capacity to allow for this nonlinear transitions, nonlinear migrations of the ITCZ, and the establishment of very strong cross-equatorial Hadley circulation. I really don't have a lot of time to go through this, but let me emphasize how this is really an important point. Circulations that remain more symmetric about the equator, for instance, as we see happen close to over the oceanic ITCZ, either in the observations, those are circulations that do not conserve angular momentum. That is to say that advection of relative momentum by the circulation is not important, and the circulations are much more linear, whereas once you're able to establish a more cross-equatorial Hadley circulation, this is where the nonlinearity in the circulation, nonlinear processes become important, and the circulation becomes much more angular momentum conserving. And so this is a schematic that we came up with a recent review paper that we published with Ruth Ging, Dave Battisti, and other collaborators, where again, we really emphasize the importance of the circulation to become cross-equatorial, significantly cross-equatorial, to be monsoon like. Again, let me emphasize how here we're not necessarily saying that all monsoons in the circulations that develop in all monsoon regions will be deeply cross-equatorial, nonlinear, angular momentum conserving. Of course, the distribution of the land masses, the land-sea contrast will play a role. But again, this provides maybe a nice framework to start looking at different properties of monsoonal precipitation, the associated circulation patterns, and how they respond to different forcings based on, again, these arguments, whether they are on a more linear regime or in a more nonlinear regime. Okay, so let me try here to summarize what I said so far. What are the implications of this emerging theoretical perspective of monsoons for observed monsoons? So let me maybe start from the last point that I mentioned here. Let me just say that really the consequences of these emerging theoretical views on observed monsoons and how they might respond to perturbations at different timescales is really an open question in the literature right now. But again, to emphasize what this alternative emerging view is, let me start from point one. Monsoons cannot be thought of as large-scale sea breeze circulations driven by thermal contrast between the land and the ocean. Monsoons are intimately connected to the tropical overturning. As regional Hadley cells, they need to satisfy large-scale constraints implicated by the energy and angular momentum budgets. Monsoon and oceanic ITCZs are manifestation of the ascending branches of regional Hadley cells. The presence of land over monsoon regions allows for more pronounced responses to the insolation forcing, which leads to more nonlinear cross-equatorial monsoonal circulations. Yes. I'm going to be going for about a half hour, but yes, if there's questions, I think this is a great point to stop, because the other thing that I want to do, which might be useful for some of the things that Spencer is going to talk about today, is to introduce one flavor of the moist static energy budget. I think that Spencer will return to this, maybe emphasizing another flavor of the same vertically integrated moist static energy budget. But yes, Dave has a great point that because this was a lot, if there is any question, probably this is a good time to take it.
Okay, so any questions?
There's one in the back.
Thank you. It's a very interesting lecture. And well, going back to all of these requisites of having monsoons systems, we already know that we need some things like planet rotations, annual insolation cycle, and all of those things. So is there any evidence for other planets having monsoonical systems?
Yes.
Like, I don't know, Jupiter or something?
Yeah. This is a great question. There are planets that do have seasonal Hadley circulations, which in fact can be broader than what we see on Earth. For instance, Titan, which is one of the moons of Saturn, is very interesting because in terms of size, it's very similar to Earth. It is a much more slowly rotator. And because, again, as Spencer said, our planet is highly rapidly rotating, what this means is that the tropics are constrained within, let's say, 30 degrees north and south of the equator. Again, Spencer said, answering one question, the boundary of what tropics, subtropics versus extratropics is somewhat fuzzy, and absolutely is. But if we use, for instance, the Rossby number as one non-dimensional number that gives us a hint as to where we can define the extratropics and where we can define the tropics. So, for instance, Rossby number, large Rossby numbers are corresponding to tropical conditions on Earth. Again, more or less 30 degrees is where the size of the tropics. But Titan is rotating much more slowly, so it's has a longer day. And in fact, it is approaching the limit of an all tropics planet. Rossby numbers are large throughout the tropics, and in fact, you see that there, in response to the insolation forcing, you can have, and this is supported by observations, by modeling evidence. Our colleague Jonathan Mitchell has spent a lot of time thinking about Titan. There, the ITCZ can almost move all the way to the poles during the summer in association with a very broad Hadley cell. And this is, your question really points to, I think, really the fundamental importance of developing theories that can really help us think about the dependence of important aspects of the Hadley cell, both in terms of its annual mean and in terms of the seasonal cycle, in terms of planetary parameters or mean state climate variables. Because again, now, of course, we have examples within our own solar system, but every day there are other exoplanets that are being discovered. And so I think it's really important to develop theories that can really help us think about planetary circulations in a much broader parameter space.
Yeah, thank you. And this brings me to the next question. Well, I have other two, which is considering like more paleoclimate, and which could be like the Milankovitch cycle approachation to all of these monsoonical systems.
Maybe you should leave that question for Spencer's talk. Spencer is talking about implications of some of these emerging theories for past and future climates. And so I think that your question, ask it again after Spencer's talk.
Well, okay, so the next question
Easy
was
for me.
related. Yeah, the next question was related to that, so I will leave it.
Sure.
Thank you.
And I will be more than happy to also give my perspective later on, but I think that Spencer is very well equipped to provide a frame his answer after presenting, again, thinking about things that we have learned through these emerging theories. Yes.
Yeah, really, really nice talk. I have a question related to why the ITC is in the Northern Hemisphere. I think in the early time of your talk, you said that it's related to the AMOC. And I think I kind of understand why, just because the AMOC is transporting warm waters to the northern side, you have more moisture available there, that increase the moist static energy. And I think that kind of makes sense in a way. But if we look for the ITC in the Atlantic, that is like the main region where the AMOC is where the ITC is even more like southern than compared to other ocean basins.
Yeah.
And a follow-up question is that I know that in future climate projections, the AMOC is supposed to get weaker. So we have like a more equatorial war ITC in future climate predictions?
Yeah. So this is a great question. I'm going to try to give a super brief answer because, again, these are things that Spencer will touch upon. But again, just to give a very, very schematic overview, let's just say that in the past 20 years, again, well, maybe let me start from the fact that we've been thinking about constraints for tropical precipitation for decades now. And theories in the 80s, in the 1980s, really emphasized the dynamical control on tropical ITCZ, going back to Lindsay and Negam, who basically developed a model that is based on, again, the boundary layer momentum budget, with the idea that regions of maximum lower level convergence, as determined by the boundary layer momentum maximum, would be regions with more intense precipitation. And all of the previous theories really emphasized a lot tropical controls on tropical precipitation, which makes somewhat sense to us. In the early 2000s, and we started thinking about convection and its interaction with the larger scale circulation drivers, theories emphasized much more thermodynamic controls. And so again, let me go back. Lindsay and Negam really SST gradients were considered very important because this is what drives pressure gradients and blah, blah, blah. Then theories shifted towards maybe being a bit more agnostic as to what the convergence is doing, with the idea that causality there becomes a bit fuzzy in the sense that where convection develops, of course, this will have to be accompanied by lower level convergence, but causality arguments, again, start being a bit maybe too strong there. The idea is that convection is associated with where instability develops, and again, convergence will follow. And so theories based on this, again, this new views of convection really emphasized maxima in sea surface temperatures and maxima in moist static energy. And you are a bit more agnostic about gradients, resulting convergence, and so on. But again, all of these theories really emphasized processes that act in the tropics, local to where the ITCZ is located. But we know, and again, this starts answering the paleo question, there is evidence that the ITCZ has shifted in response to Milankovitch cycle in the last glacial maximum. And so the question is, how can remote perturbations drive changes in the ITCZ? And this is where this energetic framework has emerged. Again, here I leave to Spencer to really explain how it is, and again, maybe go a little bit more in details as to the answer to your question. But here the idea is that the ITCZ is embedded within the Hadley cell. And as such, it participates to the global transport of energy. And so any remote perturbation that, for instance, happens even away from the tropics causes changes in transport of energy by large-scale eddies, because we haven't talked much about the extratropics here. In the tropics, it is the returning circulation that does most of the transport of momentum, of moisture, of energy. Outside of the tropics, it's all about the extratropical eddies. So again, for instance, let's suppose that you put a heating perturbation in the northern hemisphere, higher latitudes. It, of course, will have to be accompanied by a decreased flux of transport of energy by the eddies. And so that anomaly is communicated to the subtropics, and it's then up to the Hadley cell to restore energy budget. And because, and this is something that I'll show you if there is time in a minute, because again, I'll provide another flavor of this vertically integrated moist static energy budget. The Hadley cell, on average, not always, but on average, is not only a thermally direct cell, but is an energetically direct cell. That is to say that it transports energy in the direction of the upper level flow. So again, let's suppose that we put a heating anomaly in the northern hemisphere, higher latitudes. Through changes in the transport, this anomaly is communicated to the subtropics. And now it's the Hadley cell that needs to accomplish to transport away that energy from the northern hemisphere to the southern hemisphere. And it does so by shifting further poleward, if it was already in the northern hemisphere, the ATCC, so that it can transport more energy across the equator. To answer to your question, again, super quickly, as to, well, you said it's the AMOC. And so the idea is that if you think about the vertically integrated energy transport, if the ocean is transporting energy from south to north, everything else being equal in terms of, for instance, shortwave and longwave hemispheric asymmetry in the radiation, is really the Hadley cell that needs to transport energy back. Then the question, oh, but the AMOC is acting locally. But the truth is that in anomaly, the oceans have boundaries, the atmosphere doesn't. And so an anomaly can be communicated at other remote longitudes. And so we think more broadly about, again, changes that don't remain localized where the anomaly initial perturbation was. Does this start answering your question? And again, I think that after Spencer, I don't want to take away from Spencer's presentation. And so again, I think that things will become a bit more clear after his presentation. Una más, ¿sí? ¿Está bien?
Thank you, Doctor, for your talk. I just asked this question to Dr. Turen this morning, but I would like to know your opinion about the, sorry, I'm nervous, about the hypothesis proposed by Booz and Pascal regarding to the mechanical forcing of the North American monsoon, because we see the role of the Hadley cell and the thermal forcing, but they are proposed this mechanical force by orography for the land.
Yep, so thanks for the question. So I will actually let the experts here in the room, there are other experts, give their more, again, I think that their assessment is more, they know the literature better than I do. The one thing that I will say about the American monsoon is that, again, the North American monsoon is the fact that, for sure, right, I talked a lot about this view of monsoons as a cross-equatorial Hadley cell. I didn't have time to show this for the North American monsoon region, but this connection between the extension of the summer rains over the Sierra Madre Occidental, over the southwestern United States, doesn't have any connection with the cross-equatorial flow. The cross-equatorial flow and this more Hadley cell remains confined over the Eastern Pacific ITCZ. So in that respect, the North American monsoon is a bit different in the sense that I think there are more local circulations that still allow for that precipitation to migrate further northward. But I think the controls are different. And for sure, the existence of the Sea of Cortez, Baja California, the Sierra Madre Occidental, they all provide fundamental forcings for the local circulation that develops there and that allows for the monsoonal rains to propagate further poleward. The relative role of the mechanical versus the thermal forcing, I leave it to the experts. I think that the work by Booz and Pascale is, I think, very convincing, but I also probably there, again, there's other mechanisms that play a role as well. I would not discard the importance of the thermal forcing there, because again, for sure, the fact that you have this large body of hot water there serving as a moisture source, the diurnal cycle of the winds that develop over the Gulf of California in response to the presence of topography, I think those are all things that play a role there. I hope this is satisfactory. So I'll tell you a joke that my PhD advisor, Bjorn Stevens, used to make. So I worked on the North American monsoon based on observations in the first part of my PhD, and then I moved to the more idealized modeling. And so I really emphasized how, from a certain perspective, the North American monsoon looked like a monsoon, right? If you look at the seasonality of the precipitation, the existence of changes in the both low-level and upper-level circulations, they're all there. And so again, just to say that Bjorn Stevens used to laugh at me to say that I spent half of my PhD thesis trying to convince him that the North American monsoon was a monsoon, and the rest trying to convince him that it was not a monsoon. So I leave it there.
Yeah, I'll try and be super quick because I don't want to take the rest of your time away. It was just this issue of the equatorward shift of the rains with respect to the boundary layer moist static energy. You attributed it to the fact that the branch of the Hadley cell was stronger towards the equator. But I mean, I kind of take issue with that, because the upward branch of the Hadley circulation at the end of the day, that's manifested all in the upward motion within convection itself. And between that, the air is actually going down. And so basically, your argument seems a little bit circular, because you're kind of saying the convections to the south, because the convections to the south, because the upward branch of the Hadley circulation is manifested in the upward drafts. And so, I mean, my interpretation always was that it's much more linked to the ventilation and the water vapor above the boundary layer, especially in certain sectors. If you look at the West African monsoon, part of the reason why you have this shift between the ITD and
it's
the
because you have the Sahara north
Sahara air layer, which you showed was very strong and different there. So
so
for me, that shift is much more about what's going on.
So first of all, let me take issues with what you said, where you said that the ascending branch of the Hadley cell is where convection is. We have yes and no. We have simulations. We went a very, very slowly rotating planet, or actually where Earth-like conditions, you force it with the perpetual solstice. The hottest spot becomes the pole. This is where your most static energy maximum maximizes. This is where you have a ton of local convective activity, and yet the ascending branch of the Hadley cell remains constrained to be at 30 degrees because our planet is a slow rotator. So again, convection has this important aspect, right, that it can only organize itself within certain broader circulation, large-scale patterns, to the extent that temperature anomalies associated with development of that convection can be communicated elsewhere. And that is to say that, again, we can have the pole being the locus of maximum convection, and yet the convection remains local because, again, through gravity wave, that signal cannot be spread. That is to say, I mean, maybe we can take this conversation offline because there's other things. Absolutely, you're right. This theoretical framework, of course, is very coarse, not coarse, but it's very idealized. It only takes into account certain aspects of convection and not others. And you're totally right that there are much more complicated mechanisms within convection itself, the role of ventilation. And in fact, I want to mention it now, if I'm allowed, in the next few slides. But I think that this idea that convection always happens and maximizes within the ascending branch of the Hadley cell.
Okay, but it's not the maximization, but I think it's important to just emphasize, to make sure that people don't think of the upward branch of the Hadley cell as being some kind of general upward motion, that upward motion is all
No,
measurable.
this is also what I say in when I
The
teach.
example you gave, the
Absolutely,
maximum is at the
absolutely. In
source,
fact,
nevertheless-
even where convection is occurring, air on average is descending.
Exactly.
And that has to do with the fact that convection is, so there is this asymmetry. And again, I'm going to quote Bjorn Stevens again. Air goes up moist, but comes down dry. And this gives rise to this big asymmetry between much narrower and very strong updrafts and much gentler descent over much broader fractional areas. Does that make you happier?
Yeah, no, it was just the attribution
Yes,
to the
absolutely.
the Hadley upward branch. That,
Absolutely,
I
absolutely.
think is circular.
Absolutely, absolutely, absolutely. I was really focusing here on the large scale perspective that neglects and averages over the fact that, in fact, these convective scales are small scales embedded within this larger overturning circulation. Thank you for this clarification.
Thank you. Yeah, definitely. It's a cause, not an effect. Also, I would just, when you talk about your models, please tell us if you actually resolve convection, or is convection.
No, it's
Oh,
parameterized.
that's problematic.
Parameterized,
Okay, we're gonna-
parameterized.
So
convection.
we got some serious issues to talk about.
Yeah, no, absolutely. It's parameterized through a quasi-equilibrium convection scheme. Yep. Okay, so super quickly, I'll try to be quick. I'll try to use the last 15 minutes to introduce the moist static energy budget, because I do like theoretical frameworks. And theoretical frameworks, it's interesting to push them, as Dave always does, to really push them and to really understand what's the boundary, what are the limits of their validity. But they do provide some, again, frameworks to analyze observations, make sense of models that usually do not agree with each other. And in fact, they disagree more than they agree. So how do we do this? Again, this is work that David Nealon has done throughout his career. And so let's start from the thermodynamic and moisture equation. I don't want to go through the details here. I have an additional slide in case you're interested, but here I am using pressure as my vertical coordinate. And so omega represents this vertical pressure, vertical velocity, which is negative for upward motion, positive for downward motion, because pressure decreases with height. The reason why we use pressure coordinate, well, there's many reasons. When pressure coordinates, basically, our very compressible atmosphere looks like incompressible. So this makes it, for instance, continuity equation is much easier. We get rid of a lot of compressibility effects we're not interested in. And so this is just, again, the first law of thermodynamics that we looked at yesterday, written a little bit more differently. So this is the basically material derivative with the horizontal advection of temperature. And here, this term comprises both vertical advection of temperature and, again, the changes in pressure, if you follow, an air parcel. And so here, notice how in this vertical gradient term, we have both dry enthalpy and potential energy, what we call the dry static energy. This is it's an energy equation, so it has units of energy. The moisture equation, we turn it with units of energy by multiplying by LV. The latent heat of vaporization is just telling us that basically moisture can change, so the atmospheric moisture content, through either evaporation of condensate or condensation of water vapor that act respectively as sources or sinks of specific humidity. Then we're going to vertically integrate. And so this is now what we have. And so now our sources and sinks of dry enthalpy or moisture are for, again, the dry energy equation, the diabatic latent heat released through the column, so we're vertically integrating. And then we need to also consider how energy can enter the atmospheric column from the bottom and the top through shortwave and long-wave radiative fluxes and sensible heat flux from the surface. When we look at the moisture equation, we have the basically a removal of moisture, again, through condensation throughout the column, the net, of course. And then we need to take into account how water vapor can enter the atmospheric column through evaporation from the bottom. So now we sum, And we use the fact that basically the condensational diabatic heating is equal to basically this moisture sink from the moisture equation. And this is great because these are the largest terms that appear in each individual equation, but the ones that we cannot really constrain that much because, of course, how much, where condensation occurs, where precipitation occurs, depends on the flow that we want to solve for. And so we sum these two and we obtain the moist static energy budget. Again, this is a statement that any energy that is stored in atmospheric column and that is then advected around both in the horizontal and vertical direction needs to balance the sources and sinks of energy entering from the top and the bottom of the atmospheric column, what we call the net energy input. And this comprises the top of atmosphere radiative fluxes and the surface fluxes. Again, let me go back to this schematic here. These are the top of atmosphere radiative fluxes, and these are the surface fluxes. Okay, so again, this really has been used throughout really the past 30 years in many applications, both to think about steady state and large-scale circulations, but also thinking about disturbances, for instance, as the MJO that develop in the tropics, again, trying to tie up the circulations that develop to sources and sinks of energy through the top and bottom of your atmospheric column. So in the deep tropics, we can do something else because we can use the weak temperature gradient approximation. Again, we're looking at steady state, so we neglect this term. Tomorrow we'll see when and how this might not always be negligible. We also assume that because there are weak temperature gradients, advection is not large, at least in the deep tropics when we're really close to the equator. We also assume, and that is a little bit more of a leap of faith, that also moisture gradients are small. And so the leading order balance, when we take a long time mean, is between the vertical advection of moist static energy, this is our favorite moist static energy variable, and the net energy input in the atmospheric column. We're also going to assume that on average in the tropics, although now even work that Spencer is doing is forcing us to think about the role that eddies play in transporting energy and moisture in the tropics. But again, if we assume that at least on a large scale perspective, most of that advection, that transport is affected by the time mean circulation, then again, we can just neglect the nonlinear terms. And so also given that moist static energy on average is positively stratified in the tropics, that is to say, there is a mid-tropospheric, lower to mid-tropospheric minimum, but values of moist static energy tend to be higher up in the troposphere than they are close to the surface. That is to say, this term is usually negative, that is, H increases with decreasing pressure. What this implies is that regions of positive net energy input need to be accompanied by the development of upward vertical motion. Remember that omega negative means upward motion. If we further assume, and again now people are trying to think as to the consequences, the implications going beyond this simple first baroclinic mode picture of the tropical circulation, if again we assume that in the tropics, in general, motions are associated with the first baroclinic mode, and what this means is that we have temperature, that's true, but vertical motion maximizing in the mid-troposphere and being accompanied by lower level convergence and upper level divergence, then again, this is where we were talking about the fact that these circulations are energetically direct because, again, moist static energy as this structure by which moist static energy values are lower in the lower layers and they are higher in the upper troposphere, the development of, again, this diverging motions away from regions of net positive net energy input implies that these circulations are transporting energy away from regions of positive net energy input that tend to be collocated with, again, ascending branches and divergence, again, lower level convergence and upper level divergence of this overturning circulations. Okay? Okay, and so the final thing that I want to do, I hope this makes it clear. And again, there's a lot of assumptions that go in here, right? And a lot of the assumptions also pertain to the vertical structure of deep convection. We know now that we have regions such as the Eastern Pacific, the Northeastern Pacific, where this would still be a deep convective regions, but where the vertical structure is very different. And in fact, the profiles of, for instance, vertical motions remain much more bottom heavy. And in fact, this outflow here, this divergence in terms of mass is not occurring in the upper troposphere, but is occurring in regions that at levels that correspond more closely to this mid to lower level minimum in moist static energy. And so in fact, it has been shown that, again, deep convective circulations that are more bottom heavy can import rather than export energy in their ascending branches. Again, this is to say that there is a lot of ifs that go into this arguments, but again, they provide a first order view and they really allow us to understand important aspects of the tropical circulation. I want to go back to this moist static energy framework to give credit where it's due, because in reality, the need to revisit the role that lensy contrast plays in monsoon really goes back again to David Nealon. Another joke, this is a joke that I make, is that many of us working in tropical dynamics are really just rediscovering things that David figured out 20 years before us. He just didn't put them in a way that could be understood by the extended community. And so again, let's go back to the moist static energy budget, because I think that it really allows us to really clarify the role of the lensy contrast in agreement with what I showed before. So now I talked about the vertically integrated moist static energy budget, but now let's think about the surface energy budget, because of course this surface fluxes that represent a source or sink of energy for the atmospheric column are also the surface fluxes that represent a source or sinks of energy for the surface. And so I wrote the general statement that applies for the general equation that applies both over land or over the ocean. So this is the energy that can be stored in your lower boundary. Of course, over the ocean, you also need to account for the fact that energy can be uptaken not only through storage, but also through the fact that, of course, the ocean is a fluid and has this property, like the atmosphere, of transporting energy away or into some regions. And this is expressed as the convergence with the minus sign of the energy transport by the ocean, such that, again, you can have increases of surface temperature. This is the temperature representative of the mixed layer, where your oceanic circulation is converging energy, decreases where it's diverging energy. But now, over land, there is no ocean heat transport, because this term is not there. And because the heat capacity of your continent, or your land surface, is so small, if you integrate over time scales of a few days, there cannot be any storage. None, right? What this means, therefore, is that your surface fluxes are constrained to be almost equal to zero. And so if we now go back to our moist static energy budget again, in the deep tropics, and I'll show you how, well, and I'm not sure I have time to show you, but anyway, in the deep tropics, where again, we are assuming that the gradients are not important, again, we wrote this statement that energy balance requires that the vertical advection of moist static energy be balanced by the net energy input. Over land, this cannot come from the surface. None of that net energy input, for instance, associated with changes in the solar insolation, can go into energy that is uptaken by the land surface. So it's the atmospheric circulation that needs to do all of the work to transporting that energy away from maxima of net energy input. In the ocean, the atmosphere needs to do over the ocean less work, because some of that changes in the top of atmosphere radiative fluxes can be uptaken by the ocean through both storage and transport away from these regions. And this is an alternative way of looking as to why we have more more extreme, the responses over, in terms of, for instance, the Hadley circulation over the ocean is more pronounced than what we see over the ocean. So this is an alternative view of looking at the role of the Landsea contrast. And again, also to give credit where it's due to really great work done by Neeling and collaborators. And so this is a little bit of an updated figure, but again, here I want to show you, this is the net energy input from an older previous paper by Neeling for the month of January and July. And again, notice how, and again, this is really the thing that I want to emphasize, how our continents become regions of positive net energy input almost everywhere in the summer hemisphere. These are our continents. Again, sorry for this, this darker shadings represents region of positive net energy input. And notice how over the ocean, again, this is not the case. The ocean absorbs and releases heat through the course of the seasonal cycle. Focusing on Northern Hemisphere summer, and really I'll conclude in 2 minutes, focusing on Northern Hemisphere summer, let me emphasize how basically we see that almost all of the continents, not just in the tropics, but over the continents, we have positive net energy input, except in desert regions. And that is because these desert regions have such a high albedo that a lot of that incoming energy is not made available, but is reflected back to space. And that is one reason why we think that, again, there's a lot of interesting features that arise because of the presence of these deserts poleward of, for instance, the Western African monsoon. That said, again, we revisited the role of the Landsea contrast from the perspective of the moist static energy budget, but also this distribution that I just emphasized clearly poses another question. The net energy input is large and positive over the land masses, significantly poleward of the convective zone boundaries. And so why don't we have monsoonal precipitation that extends all the way to the pole following the net energy input? And I think that this is exactly where this discussions as to the fact that our tropics are somewhat bounded by within certain latitudes from the equator come into play, because of course, as you start moving away from the equator, your temperature gradients are no longer negligible. And in fact, even more, your moisture gradients, let's just say that moisture gradients even in the tropics are not that negligible. And so this is where ventilation comes into play. This is a term that Adrian used. And basically, as you start moving away from the deep tropics, ventilation of low moist static energy air from the colder ocean really plays a very important role in not letting that convergent zones migrate into, let's say, extratropical continents. And again, that import of low moist static energy air kills basically the convection. For the Western African monsoon, in reality, is more this large albedo over the Sahara with strong reflection of incoming radiation. And let me show you here, this is just a schematic that David put together for a very nice chapter that he wrote for proceedings from a conference that TAPI organized, I want to say in 2004. And then the proceedings were published a little bit later. And really here, it just schematically showed what happens to the extent of the North American monsoon if you suppress this ventilation, this import of low-level moist static energy. So this is a simulation that is done with their QTCM, an intermediate complexity model. In the absence of any ventilation, this is where the boundary of precipitation would be. So you would see precipitation extending much further forward. As you switch on ventilation, you see the margin of this convective region basically retreating equatorward. Notice how this is a very simple model, very coarse resolution. So one could argue to what extent this is, in fact, well reproducing the climatology of the North American monsoon. In fact, it doesn't, right? It doesn't capture how it extends much forward. But again, it is really that's why I really myself like intermediate complexity models or idealized models, that you shouldn't take them as a way to really reproduce all the features you're interested in, but really They are great at testing hypotheses and mechanisms. I think I'll skip this because I don't have time. I'll pull up my summary. Again, this is a summary that I emphasized, that I showed before, again, just to emphasize that I think that despite some limitations, these theoretical frameworks really give us a lot of food of thought to think about fundamental workings of monsoons and how they might respond to different perturbations. I'll stop here and thank you for your attention.
Okay, yeah, so we'll have some debates. Let me make sure I stand in the camera when I say this one. Is Lindzen still a climate denier? Global
Oh,
warming denier?
I absolutely. I think he got worse
Okay, all right.
through the years. But I think he's retired now. I've stopped following him, I have to admit.
Okay, well, we'll talk about also conservation of England. Okay, anyway, so we got about, what, 25 minutes for a
Minus
break?
3 minutes for questions.
Okay. Oh, I'm sorry, yeah, you want to do some more, you guys want to do some more questions?
We can do questions, or we can
okay.
bring the discussion to the
All
coffee
right,
break.
let me ask that one then.
Okay.
Just one other quick announcement before we start.
This working? Okay. Now you want? Yes. Whenever you want. I can start whenever you want. So, so good morning, everybody. Can you hear me? All right. So my name is Alejandro Jaramillo. I'm part of the local team. And today I'm going to, let me check this. No. I guess this is better, I guess. And today I'm going to talk about tropical waves. Actually, this is a very basic introduction to tropical waves, and I'm inspired by a very popular series of books. You may see one of those books that is the series of Something for Dummies. So this lecture is going to be something like Tropical Waves for Dummies. Of course, this is not sponsored by Wiley, but if Wiley wants to help us in the next seminars, we will be happy to receive your help. So this is going to be a very basic introduction. Actually, this is perhaps the lecture in this workshop that is slightly more off topic. I will try to connect what has been talking in the previous lectures. So the first, or to start talking about tropical waves, we must go around to a very different question, and is how tropical waves are tied or are connected between weather and climate. And I assume that most of you know the difference about weather and climate, but we have a very basic idea of the difference, because weather, for example, tell us what kind of clothes can we use today. For example, if today is going to be very cold, we are going to use coats, sweaters, and all that kind of stuff. If it's got hot, we use t-shirts, shorts, sandals. So the weather tells us what's happening right now, but the climate tells us the kind of clothes that we have in a season, for example. So in winter, we probably will have in our closets more warm and cozy clothes. So this is a very rustic definition of weather and climate, but these definitions are very related with the notions that we have about seasons. For example, here in Mexico City, we still notice the difference between the seasons. For example, spring is clearly very different to winter in Mexico City. But if we go deeper into the tropics, and some of you come from countries very deep in the tropics, you know that this seasonal difference is not that strong. And the seasons and our climate in the deep tropics, it's from going to very rainy days to slightly less rainy days. That's like the main difference of the different climates in the tropics. But we all have this rustic idea of weather and climate. And if we want to go to a very textbook definition, we can go to this very beautiful book by Herberson at the beginning of the 20th century. This is a very, very nice, very interesting book. You can find this book online for free. And this book has one of the most popular sentences in atmospheric science that says that climate is what on average we may expect, weather is what we actually get. So we think of climate like somehow like a statistics of weather, but I must clarify that this difference between weather and climate is actually artificial. And this difference between weather and climate actually comes from our efforts to make forecasts. So we have weather forecasts, and we know that when we are forecasting weather, our forecast is really good for the first few days, but after some days, the accuracy of this forecast decreases and loses validity, is not good enough. And if we want to do climate forecasts, we need our models to warm up, to adjust to the external, to the forcings and the boundary conditions. So the models needs like a preparation time. So the climate forecasts are generally impractical for periods shorter than 3 months. So it's like a disconnection between these two time scales, and what's happening between these two time scales is what we call intraseasonal variability, which is like all the phenomena that is happening between these two time scales. So it's actually very important to connect these two like forecasting worlds that are actually disconnected, but not by actually physical reasons, but for or difficulties in connecting these two scales. Okay, so I'm going to try to understand or to explain to you how tropical waves appears in this discussion. So let's use a time series of any atmospheric variable in some place on Earth, and let's suppose that this is some temperatures in a place in the northern hemisphere, and you can see that this time series of temperature has a very interesting pattern, and we want to understand what process produced this pattern. So we know we had some ideas, and first we know that there are some balance of energy, some incoming radiation balance, the outgoing radiation, and this balance produce like a mean equilibrium value. So we can draw here like a mean value around this picture, and this mean value is basically explained by this energy balance, and actually this line explains a lot about the behavior of this time series, because all the values oscillates around this mean value. So the energy balance explains this solid or this horizontal line. But we have times of year that we have temperature below this mean, and times of the year that we have temperatures above this mean, and we don't need a Nobel Prize to know that that's related to the seasons, to the transitions, or to the motion of the air around the sun that produces the different seasons. So if we have this mean value associated with the energy balance, and we have the seasonal cycle, and we add these two lines together, we have a way better explanation about the original time series, but we still have some oscillations about that smooth line. If we remove that smooth line, we see that there are certain oscillations, and if the oscillation or the translation of the air around the sun explain a lot about the behavior of the original time series, we can try to understand this behavior using different kind of oscillations that might explain that phenomena. So if we get the two original lines, the horizontal and the seasonal cycle, and we add more waves to that sum, we'll end up with something that starts looking more and more similar to the original time series. So our explanation to what's happening in this time series might be related with some kind of oscillations. We must discover what are those oscillations. And if we keep going, probably we will get closer and closer to the original time series. Actually, this is the principle that is used or that is discovered by Fourier. Joseph Fourier show that any continuous function can be written or decomposed into sine waves as a combination, a linear combination of sine waves. So if we have a time series, a continuous function, using a Fourier transform, we can find what are exactly the frequencies that compose the original time series. And with these frequencies, we can know the waves that sum together exactly explains the original time series. Of course, if we apply this to our original time series, we do a Fourier transform of this time series and we remove the mean and the seasonal cycle that we already know what's explaining that oscillations, we end up with this Fourier transform, and there are something very interesting. There are some spectral peaks in this time series that are telling us that to explain this time series, there are some kind of oscillations that are in very, very specific periods. So they have certain frequencies, very specific, and that phenomena is explaining the intraseasonal variability that is happening in this original time series. So our quest starts by looking what are those waves? What are the waves behind those spectral peaks? We right now don't know anything about the tropical waves. So we know that we need to look for something that looks like a wave and that will explain this original time series. And all these quests perhaps starts way before Matsuno, but like with the works of Laplace, but the most recent one and the most well-known relative to us is the work by Matsuno in 1966. In his paper in 1966, he studied the tropics, and he took the equatorial band. He placed like a beta plane, so he used the tropics like a plane, and he simplified the equations of motion by doing some simplifications. One of the most important simplification, he's assuming that the atmosphere behaves like a shallow water model, like the atmosphere behaves like a pool, for example, where the dimensions or the vertical dimensions are smaller than the longitudinal dimensions, which is not really a bad approximation because our atmosphere is actually really thin. we compare with the horizontal dimensions. So Matsuno simplified the equations, and using these equations, he showed that the only possible theoretical solutions to these equations of motions are certain kind of waves. Actually, just a very few kind of waves. The solutions to these equations of motions are the Kelvin wave, the Rossby equatorial wave, the inertial gravitational wave, and the Miss-Rossby gravity wave. These are the only possible solutions in this model, and these waves have very specific dispersion relationships that are the fingerprints of each wave. So each wave has a very specific wave number and frequency, so we can differentiate the behavior of each wave from one another. And the waves have behaviors like some of the waves move only to the east and some waves move only to the west. So Matsuno ended up finding theoretically that in the tropics it's possible to have waves that are trapped in the equator that move to the east or move to the west, but only 4 kinds of waves. And also they have meridional structures that can be symmetric or antisymmetric about the equator. So Matsuno found that there is possible to have waves in the tropics, but they don't look like this. They look more something like this kind of animation of waves moving in the tropics. And so this is part of theory. We found empirical observational evidence of the existence of these waves first in the stratosphere, but in the troposphere, I'm going to wait a little more slides to find these waves in the stratosphere. This is only theoretically, but it's important. What may cause this kind of waves in the atmosphere? What kind of forcings can produce waves? One of these forcings can be orographic forcing. So the orography can force the air to go up and down, and that can produce oscillations in the atmosphere. They can produce waves in the atmosphere. For example, there is a very beautiful example of waves produced by the Ista Seawald some days ago. That actually this is not an equatorial tropical wave, but it's a beautiful example of a wave produced by topography. So if you are lucky enough, perhaps this week you might see this kind of clouds in the sky. And these are more common. You can see this kind of waves if you pay attention to the clouds. Or a beautiful example, not a tropical wave, but one of the most beautiful examples of waves produced by topography, like the one by Guadalupe Island near the coast of Baja California. The topography produce very beautiful waves and other vortex, like Kelvin von Karman vortex too, associated with the motion. These are not picture of tropical waves, excuse me for that, but they are beautiful examples of waves produced by topography that some of them can also be tropical waves if occur in the tropical regions. What other kind of forcings can produce waves? In particular, what kind of forcing can produce waves in the tropics? And here comes a work that Cuauhtemoc mentioned yesterday. There was the work by Gill, and he showed, using a similar model like Matsuno, a numerical model like Matsuno, that diabatic heating forcing can excite tropical waves in the atmosphere. And we know these kind of models like Matsuno-Gill model, and this is very important because we have topography that can produce waves, but we can have diabatic heating producing or exciting waves in the atmosphere. Remember that at this point, this is completely theoretical, but this opens the connection to the workshop today because we have important mechanism that can produce a kind of diabatic heating. And that mechanism is deep convection. Deep convection can produce this kind of diabatic heating, the latent heating release in these clouds, and the forcing that these clouds can create in the atmosphere can excite waves in the atmosphere. Or, of course, this is a simplification, or oversimplification, because Dave is looking like, ah, I'm going to kill you. But, okay. So convection can produce this kind of waves. So it's very important, like convection is like a key ingredient to try to find the waves that we need to find, that our quest requires to find in the tropics in order to explain the intraseasonal variability. So it's trying to be like slightly historical accurate in the tropics, like the first evidence of this kind of waves were like the easterly waves, that's some waves that are produced in Africa and moves to the west. Here's an example of this wave. You can see the wave pattern here. And these the easterly waves are perhaps first known because they are very related with the formation and the initiation of tropical cyclones. And that's perhaps why they were first discovered. And actually, these waves are really important. For example, a work by Christian, who's going to give a talk next to me. She found, like, for example, in this region are of interest, precipitation, summer precipitation are very associated with easterly waves. In some places, it's higher than 40% or even 50 or 60% of the summer precipitation is associated with easterly waves. So easterly waves are really important, in particular in this part of the region. And of course, not all the easterly waves are formed in Africa. There are some easterly waves that form here in this region of the Pacific, but that's another topic for a different workshop, I guess. The next wave is very important because this is very close to Matsuno's work, is the conversion work of Madden and Julian, because they found one of the most important oscillations in atmospheric science. And this work is actually really important if you see the background of how they discovered this wave, because it was a time when they only have radio zones. Actually, they were not radio zones, they were Ramin zones, actually. And these observations, they have observations, but also the computers started or appeared in this scene, and algorithms, like, for example, a new algorithm to do Fourier transform. So these two convergence of observations and new algorithms and computational capabilities allowed them to use observations in the Pacific and found a very strong signal showing that there is something happening in that observations that can be explained by a phenomena that has a period of 30 to 60 days. Something was happening there. Remember that this was prior to the satellite era. So this is very, very, very a big goal. They made a really great work because they extended the analysis to cover all these station sites, and they found that actually that strong signal
I'm curious about why don't take why the in the equations don't take into account the non-linearities of the advection term in the momentum balance, and also why don't take into account these fluxes of momentum of energy, these covariance that is the fluctuation of the vertical velocity and the temperature, which is related with the tensors, the Reynolds tensor, stress tensor. Why don't take into account these fluxes of energy in the vertical components? That's the trick. The questions.
What you mean about the Matsuno model, or?
No, the divergences of these of the product of these vector velocities, which is the non-linearity term. Do you understand what I mean?
Yeah, yeah. Actually, yes. The Matsuno model is a very simple one. Actually, they remove all these non-linearities in the equations, because that's the only way you can have analytic solutions, and like these solutions. But take into account that these kind of waves are synoptic scale, and in this scale, some approximations work really well. So we still don't need the non-linearities, so we can work with a very simple linear model to produce these waves. Of course, there are non-linear interactions between these waves, but are like what's only in that region. That's like the main explanation about that. So what's happening?
Seguir haciendo las preguntas porque
Oh.
se desconectó la red y están tratando de reconectar.
Okay.
Entonces, pues vamos a seguir. Pero bueno, te damos. Okay.
No.
Es que para que, bueno, ya es cierto, no están en línea, no están en línea, sí es cierto. Bueno.
Thank you very much. And I know maybe this is not the main idea of the presentation, but regarding this maiden Julian oscillation, I would like to know if there is any positive impact regarding the amount of precipitation that we expect in our country? Or
Yeah.
is any
Yeah, actually, that's what I'm going to do at the end of the presentation, is going to show you something about a very glimpse about that. So just wait for a second. Okay. Okay. I guess
Ya hemos vuelto.
we can keep going, or okay. So we were somewhere from here. So we found the evidence. I was saying that, for example, I guess I was exactly at this point where I was mentioning, or I was trying to mention that, for example, this spectral peak here, we have very strong, we know with strong confidence that should be related with Kelvin waves. Also, for example, this should be related with equatorial Rossby waves, and so on. So the Matsuno's waves are actually real in the troposphere. They were real in the stratosphere first, but we found evidence that they are real in the troposphere, although they are much hidden in the intraseasonal variability, because all the phenomena like the Madden-Julian oscillation dominates that variability. But they are there. So if we filter the data, we can see anomalies associated with those waves in the original OLR time series. So the important point here is that we have these waves that exist in the tropics. So we now found the waves that will help us to understand the variability. That we start looking at the first place, at the initial, and at the first place in this lecture. But it's important that now we want to use these waves, or the knowledge about these waves, to try to understand other weather phenomena. So we want to know, for example, what happened with precipitation associated with these waves. So we try to do some causality relationship between, okay, this wave can help us produce precipitation, but we must be very careful, because sometimes we tend to say, okay, the Madden-Julian oscillation is producing precipitation here, 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 and we actually try to associate everything with Madden-Julian oscillation, but not necessarily the Madden-Julian oscillation is producing the event or is producing the precipitation. Unless you are in the maritime continent and the Madden-Julian oscillation is about you, it's of course the Madden-Julian oscillation that is producing the precipitation where you are. But for example, here in Mexico, we can relate the Madden-Julian oscillation or these tropical waves to precipitation, for example, but we must recognize that there is not necessarily a direct cause effect. So not all Madden-Julian oscillation produce precipitation here, but they are related. And they are related in a sense that, for example, the Madden-Julian oscillation may not produce certain effect or certain weather event, but they might influence the likelihood of its occurrence, or its intensity, or its spatial patterns. It's something, for example, like with climate change. We cannot say that certain hurricane, for example, is produced by climate change. Of course, there are some effects of climate change that help to produce certain, for example, hurricane, but a hurricane may exist in a planet without climate change. So it's the same. We must be very careful when we are studying the relationship between the waves and the weather events, because we must be more open-minded about these kind of relationships. So this is the kind of studies that we know that we have this interseasonal variability associated with these waves, and we want to understand how they are related with the phenomena we study, for example, here in Mexico and other countries. So we must know that these waves can produce a direct effect on precipitation, for example, when you have the Madden-Julian above you in the maritime continent, but there are also some teleconnections of these waves in particular the Madden-Julian oscillation, which is the dominant one. And there are different mechanisms by which these waves can help produce these relationships between the events and the wave. For example, by modifying the strength of overturning circulations. For example, the Madden-Julian oscillation in particular can modulate or influence the Hadley circulations, and they modulate the monsoons in different places of the Earth. Of course, the monsoons exist per se even without NGO, but the NGO can help modulate part of the activity of some monsoons. Of course, they may create changes in moisture transport, so they may help, for example, make more moisture available. And you have more moisture available, it will make more probable to form deep convection in certain place, or they can take the moisture away and it makes harder for convection to develop in that region. There are, for example, tropical wave trains that can start in the tropics and move into the exotropics. This is, for example, you know perhaps about the Pineapple Express. So Madden-Julian oscillation, for example, can excite some Rossby wave trains that can move into the exotropics, and they can influence, for example, atmospheric rivers that hits California, for example, producing flooding in that regions. And of course, the most interesting part, because this is something actually very nonlinear, is that the wave itself can excite other waves that can interact between each other, so they can produce like strong or regions when high precipitation is more probable. These are just a few mechanisms where there might be teleconnections of these waves with the precipitation. And usually, what we do when we study the connections is that we try to connect the phenomena that we are studying. For example, I want to study precipitation in one place in Mexico, or in one place in South America, wherever you want. So we try to connect that behavior or that phenomena, trying to tie that behavior, what is happening with an oscillation, for example, with the Madden-Julian oscillation. And you usually organize or divide the Madden-Julian oscillation in phases associated with the location of the main convective center of this oscillation. So for example, we call phase 1 when the oscillation is developing here in the Indian Ocean and is moving. Phase 3, 4 is here in the Indian Ocean. 4, 5 is here in the Maritime continent. 6, 7 is here in the Pacific Ocean. So we try to tie our phenomena with what's happening or the location of this oscillation, because it will help us to try to understand what's going on, for example, here in Mexico. So if the oscillation is located here, or the main convective center, it's located here, this convective center and its oscillation, and it will change the atmospheric circulation here in a certain way that is different when the main convective center is located here in the Pacific Ocean. So that's like one of the most typical way we approach to the relationship of these oscillations with different phenomena. For example, this is the question you were asking. Donald et al., for example, they studied how the Madden-Julian oscillation influence precipitation in different parts of the world. And we can see that, okay, blue, it means that there are enhanced rainfall. Red color means that is suppressed rainfall. So more rainfall, less rainfall. And we can see, for example, if we focus on Mexico and Central America, for example, this, when the oscillation is in phase 2, for example, all this region has enhanced precipitation. But when we are in phase 4, for example, look at this. It changed. All this region has suppressed precipitation. So there is a relationship. There is a teleconnection of what's going on in the Indian Ocean and what's happening in Mexico. And look that this same kind of pattern changes are very similar in different parts of the world. Like, for example, here in East Asia, and look at this. For example, when different phases of the oscillation. So we are going to explain today, I'm going to end up with an example of a work we did here. This is part of our group. It's not all the people of our group, but some of the actual students. And I'm going to talk about the work of Lisette, her master thesis, that she studied actually how the Madden Julian influenced extreme precipitation in Mexico City. So I'm going to give you a quick background. Here is Mexico City, when we are right now. So most of you don't know, we are, I guess, if I'm not wrong, I'm like somewhere here, I guess. So we are here at UNAM here. So this is Mexico City, but this is actually the metropolitan area of Mexico City. It's composed with different, not only Mexico City as a state, but also parts of Estado de Mexico too. So it's actually a very, very big region. And Mexico City and the Valley of Mexico, the precipitation is something very important to us. Because perhaps you don't know, but this city used to be a lake. When the Spaniards, when Hernán Cortés came here, in the first place, most of you who are not Mexican don't know this. So this part of history is interesting for you. This is what used to be Mexico's downtown. This is the Zócalo, or where the Zócalo is located right now. And this is what Hernán Cortés found when he arrived here 500 years ago. So it's a very big city in a lake. Actually, to know the dimensions of this city, London was smaller than Tenochtitlan at the time of Hernán Cortés arrived here in Mexico City. So in the conquest, the Spaniards' conquest, they founded Mexico City over what it was Tenochtitlan. So Mexico City started here, and this was the lake system that existed around when the Spaniards came into Mexico, to Mexico City. But the city started growing up, and with the centuries, they have a lot of problems with flooding. So they decided to drain the lakes. And after a few centuries, this is what remains of the lake system. And yeah, you can see a little bit of the lakes, for example, Xochimilco. If you go to the Tlajineras, for example, or the Texcoco Lake, that actually is not a lake anymore, where it was supposed to be the airport that never was. So we don't have the lake system anymore. But just to have a picture, a mental picture, 100 years ago, there were still boats that went from Xochimilco to the Zócalo, for example. So the main drainage of these lakes were about 100 years ago and 50 years ago. What happened with this lake system was something very simple and straightforward. We have a big population, actually. This is the population in the official census of Mexico and the Valley of Mexico. 21 million inhabitants. This is probably close to the population of most of your countries from you came from, or perhaps half the population of the country. So for example, Colombia is about 50 million. So Mexico City, or the Valley of Mexico, is about half the population of Colombia. So it's one very crowded city. And we have very strong precipitation events that creates a problem for this population, because every time it rains, we get flooded. And it's actually very logical, because we are in a lake. So the city forgot the lake, but nature doesn't forget that here it exists a lake. So we have a lot of problems with flooding 100 years ago, but today. This is pictures from last year floodings here in Mexico City. So actually, you are in the best time of year to visit the city, because when in the rainy season, there is nothing much to do. If you want to move in the city, metro collapse, everything is flooded. So it's not very nice to do tourism in the rainy season. So it's very important. And what Lisette and we did is that we studied the extreme events in Mexico City. And look at this. Most of the extreme days in Mexico City happen when we have an active NGO event. When there is an inactive NGO, so when we don't have NGO, there is still extreme events, of course, but it's more probable to have extreme events when the NGO is active than when it's inactive. So there is a modulation of the NGO, is a clear statistically significant modulation that says that, of course, we can have extreme events anytime, but if you have an active NGO, it's more probable. And also, if we go deeper, I mentioned that we can relate this with the different phases of the oscillation. We can go and see what happened with extreme days when we have an active NGO event. And look at this. Although there are a lot of variability, there is a clear difference between phases 1 and 2, and for example, the other phases, for example, 4, 6, 7. So although I say again, we can have extreme events anytime, there are slightly more chances to have an extreme event when we are on an active NGO phase in phases 1 or 2. So when the NGO is in the Indian Ocean, when the deep convective center of the NGO is in the Indian Ocean, when it's starting and is increasing or is developing the NGO, we have more chances to have something happening here in Mexico City that increase the chance to have an extreme precipitation event. And what is the teleconnection? So I'm going to give you just, for example, this is very consistent with Donald's results. Look, Donald found, for example, that in this region, it's more probable to have rainfall or more rain in phases 2 than in phases 4, for example. This is something similar, although we are studying here extreme events, but in a much finer detail. And what's happening in Mexico City is that actually the NGO is changing something, and you see this is OLR, this is precipitable water, and this is integral divergence of moisture flux. And what these bars are telling us is that when we are in phase 1 and 2, something is happening in this region that increase moisture. Something is bringing moisture into this region, and if we have more moisture, then you have more chances to develop the convection, although the NGO is not creating the convection, is allowing to have more fuel to develop local the convection. And this is related, I guess I don't have more time. So this is related with moisture fluxes, particular in the Caribbean region. We have here a Caribbean low-level jet that brings a lot of moisture into Central and North America, but the NGO modulates the direction of the direction and the intensity of this flux. And so how during phase 1 and 2, there is a slightly change in this flux that allows the moisture to enter directly into central Mexico and enters into Mexico City. That explains, for example, what's happening, or that's a partial explanation. Of course, this work goes much deeper, but this is like a glimpse of the main explanation. That, for example, Madden-Julian oscillation is connected to the events in Mexico City through changes in moisture fluxes in this city. So, in summary, I guess that these are the 4 simple key ideas. Tropical waves are a key piece to connect weather and climate. I hope today you have a more clear idea of the connection or the difference between these 2 time scales in forecasting and why there are like this gap between those 2. And in this gap, there is the intraseasonal oscillations. There is a transitional case in the tropics. There are waves that are produced, these intraseasonal oscillations, and these waves are trapped in the equator, and moves east or it moves to the west. And these waves include the Matsuno waves, the Matsuno solutions, but also the easterly waves and the Madden-Julian oscillation, of which is the dominant one in the transitional variability in the tropics. Of course, these waves can influence rainfall, even at distant regions, even in the extratropics through atmospheric teleconnections, but it's important to mention that we must be careful when we are associating causality of these waves, because not necessarily the waves create the phenomena that we are studying, but the waves can create just favorable conditions for this phenomena to develop. If you don't have if you have the favorable conditions, you may or you may not have the phenomena happening, but you have something that may help when the waves are present. We have highlighted some possible teleconnection mechanisms, but still, obviously, there are other possible mechanisms. Some of them may be unknown yet or not fully understood. And of course, the final is how to understand how the NGO, for example, or these tropical waves influence our phenomena. So we need, for example, to study what happened with this oscillation. For example, for the Madden-Julian oscillation, it's very easy to define phases. For the other ways, it's slightly more difficult, but it's also possible. For example, that's part of Lisette's PhD thesis. But it's like a starting point to do analysis associated with tropical waves with a phenomena like, for example, precipitation or extreme precipitation or any variable that you want to study. That's all. Thank you very much. I apologize because this is a really, really deep topic, and I didn't mention all the works, of course. I just gave you a glimpse of some of the works that may lead you to start learning more about this topic, but of course, there are a lot of works that I didn't mention, but they are really important for this topic. So thank you, and I guess we have time for questions.
questions?
Thanks for the talk. I think I have few kind of related questions. The first one is about, I know that most of the tropical waves, they say that they are like convective coupled waves, but I know that from the theory itself, you can develop the waves in dry dynamics. Um so how, when does the convection or like at which time of the wave lifetime they couple with the convection properties? And the other one is for the MBO specifically. I know that the OLR usually doesn't cross like the entire globe, but other variables like I think it's potential velocity. There is a measurement between a 50 HPA and 250 HPA winds. Those usually cross the globe. So yeah, like for example, here in Mexico City, do you think that is more viable to use OLR rather than velocity, for example, for making the correlationship?
Okay, I'm going to answer your first question, and then I will try to understand the second question. But the first question is very important, because Matsuno, what actually did, it was a very simple model, a shallow water model. So actually, in water, we have a, how do you say, Dave, an interface between air and water. How do you call that? A free surface. You have a free surface. In the atmosphere, we don't have actually a free surface, but the Matsuno model is just a very simplification of the troposphere. But in the atmosphere, we can have internal waves, but we actually don't have a free surface. So the model of Matsuno, that is actually only the first version of the Matsuno model, or the starting point of the Matsuno model is only horizontal, because it's this shallow model. But if we want to study the atmosphere, we need to couple these equations to a vertical structure. So we need like a vertical connection, and that connection is a variable that is called the scale height. The scale height is basically this connection between the horizontal motion and the vertical equation, but it's related with these waves that are like internal waves when we study in the atmosphere. And then I didn't mention this, but this scale height of the equation, this connection with the vertical dimensions, is connected with the speed of the wave. So you can have very fast, large scale heights produce very fast waves. Short scale heights produces slow moving waves. So if you study, for example, in the stratotropics, these equatorial waves, you find dry waves. Dry waves that moves actually really fast. But what I didn't mention is when Wheeler and Kiladis found this dispersion. These lines, I hide something from you. These lines are the dispersion lines of the Matsuno solutions, but with very, very short scale heights of like 15 to 50 meters. So it means that these lines, for example, this line represents the dispersion curve of a Kelvin wave in an equivalent atmosphere, very, 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 very shallow. But that speed, or that wave speed, is actually the one that we are looking here. So what Wheeler and Kiladis found is that in the OLR, when you see convection, you see these Matsuno solutions, but with very, very shallow scale heights. So it means that in a nonlinear relationship between the wave and convection, the convection slows down the wave. How? We don't know. I guess that's one of the main difficulties is studying tropical waves, monsoon waves. We still don't know really well the mechanism. Perhaps Simona can say just a little bit about this. We still don't know really the mechanism that makes these waves to slow down, but it's a connection between convection. And I guess that's like your first question. So the second question, could you say again?
Yeah,
please?
so well, I'm coming from a context of hurricanes, and for the Atlantic, I know that for understanding the relationship between MJO and hurricanes in the Atlantic, they usually use another variable of the MJO that is called velocity potential, because usually the OLR signal kind of disappear in the middle of the Pacific. I was just wondering if have you tried to use velocity potential or
Velocity.
any other variable for the MGO here in Mexico City?
Yeah. Velocity potential, you say. Okay. Perhaps I'm going to give you a wrong answer, but what I think is we usually try to use a variable that is the most related with the phenomena that we are studying. So if we want to study convectively coupled equatorial waves, there are these Matsuno solutions, for example. We want to use variables that are directly related with convection. But if we want to study a different phenomena, we may use a different variable. For example, if we want to study easterly waves, perhaps velocity potential or vorticity could be a way better wave if we are not interested only in the couple with the convection, but we also want dry waves, for example. So it depends on the wave. So if we want to study precipitation, we can use velocity potential. For example, you use velocity potential, you might see other waves that are not coupled. And you want to like filter those waves. And one simple way to filter this kind of phenomena, non-related convection, is just using variables strictly related with pure convection. That's like the most simple answer. Perhaps not the right one, but okay.
I think we should probably stop here. I just, one comment, Alejandro, I would call it maybe equivalent depth
Equivalent depth,
instead, not
yes.
scale height.
No, yes, it's right. It's equivalent depth, yes, you're
The other
right.
thing, just say real quickly, you have 10 seconds. When we learned Kelades did their paper, what was the variable they used to be able to derive the different phases of their oscillations, or their waves? What data did they use?
In their paper in 1999, they didn't define phases. They found these signals in the OLR.
Okay, so I wanted you to say that. So remember when I was talking yesterday about the using remote sensing data, they use basically satellite data. So cloud top temperature, for example. Okay, that's all I want to say.
Okay.
So this is very nice about the work on the influence of the MJO on the extreme precipitation in this region. And so the way I always understood it, and tell me if you're wrong, is that usually you do not see strong convective anomalies that travel all the way to the Eastern Pacific associated with the MJO, but usually you see a signature in the dynamical fields. Is that the connection that you're trying to make there? That you think that those dynamical signature that influences the moisture transport and that influences the...
Yeah, that's right. The convective signal of the NGO lives in the Indian Ocean and dies in the West Pacific Ocean, but the perturbation still goes round the equator. So here in Mexico, for example, we don't have a direct effect of the NGO. So we don't have the NGO convection over Mexico, but we have the influence of this wave that may enhance, for example, more like, for example, in summer, for example, is related also with, well, not in summer, for example, in the spring is related with more like radiation that came into the city, for example. So it's not a direct connection, it's a teleconnection associated with this wave or the signal or the way that the convection died, but the signal still goes around the equator.
Thank you. Very, very nice talk.
Thank you.
Yeah, thank you. Well, I understand that Coriolis is extremely important for this theory, but I would like to know if, well, we know Coriolis is affects the x and y axis, and on the zeta, on the z, we have like the outpost effect. So, is there any chance this effect makes something to propagate these waves and to move them, I don't know, from the troposphere to the stratosphere, or is it also, or it could also be neglected?
You mean the Coriolis effect in the vertical? Or what do you mean?
In the z,
Yeah, in the vertical direction.
yeah.
So we have a Coriolis effects on the horizontal, and that creates the motion like in the northern hemisphere to deviate to the right of the motion. And in the vertical direction, if you move to the east, there is an effect, an apparent effect on the weight of the motion or the object that is moving. But actually in the atmosphere, that effect is less important than, for example, the horizontal effect, because the atmosphere, at least in the synoptic scale, is very is very like stratified. We have like hydrostatic balance on the large scale. So therefore, the vertical motions are not, they exist, but they are not as important as the horizontal motions in the synoptic scale. That's the reason that we ignore that part of the Coriolis in the vertical dimension. Is not as important as other effects. In the tropics, the main thing is, for example, out of the tropics, the Coriolis force is very important because there is a very important balance between the Coriolis force and the pressure gradient force. But in the tropics, the Coriolis force is very small. So this balance doesn't work really well in the tropics, although this geostrophic balance is important. At least that's what Raymond said, and though Dave don't want to mention.
Thank you. And that brings me to other question. Well, we know that these waves are trapped in the equator. So, well, out of the equator and at higher latitudes, is there any chance to develop any other kind of wave theory for that? Or are all of the perturbations related to these wave trains?
Yeah, out of the tropics, we have a very different world, to say in a certain way, because, as I mentioned, this geostrophic balance plays a very important role out of the tropics. Therefore, the kind of waves that forms in the subtropics are certainly more. I don't know how to say that right. We found waves in the subtropics first than finding waves in the tropics. It was more easy to find waves in the subtropics because this geostrophic balance creates a very special kind of waves that are very, very clear. Like, for example, the Rossby waves. The Rossby waves in the subtropics is a clear example of a subtropical wave geostrophic balance plays a very important um, um, a very important role in that wave. And we have like an equivalent slightly causing, that is the equatorial Rossby wave, that still has some kind of geostrophic kind of balance, or is a part of this structure, but it's not as strong, as big as, for example, these monstrous Rossby waves that forms in the subtropics. So in the subtropics, of course, we have, I guess that's the question, in the subtropics we can have waves, although the beta plane approximation, or the plane approximations, doesn't work really well out of the tropics, although you can still do some plane approximations in certain regions. If you take into account the Coriolis force in the correct way, you can work something similar to Matsuno out of the tropics, but it's actually not the way we do outside. Yeah.
Study waves, you can run this very simple shallow, not run, but solve for the waves in this very similar shallow water model on the F plane. And then you have the inertia gravity waves that are fast, non-geostrophically balanced, divergent waves. And then you can show that another solution is a standing mode that is geostrophically balanced. And there is the F-plane equivalent of a Rossby wave. Of course, to get a Rossby wave, you need to go to the beta plane. But basically, you can basically build these arguments where in the extratropics, you have this broad separation in terms of frequency between the fast, non-geostrophically balanced waves that are the inertial gravity waves, and then you have the much more slowly geostrophically balanced Rossby waves, which is also explains why, for instance, our motions, the planetary scales, are in geostrophic balance, because you excite all of these different modes, but the fast modes propagate rapidly a wave. They don't carry with them potential vorticity, and what we're left with are the weather maps that we see are geostrophically balanced flows. In the beta plane, in the tropics, this separation is not clear. You fill the gap with mixed Yanai waves. That is another big difference between. And so again, as you said, the tropics is a bit more complicated because there, the modes don't have a clear separation. The synoptic scale variability that makes the weather is composed of many different modes. And so that is also why we had to dig a little bit harder in the observations to find those.
Yeah, you need to filter a lot to see these waves. I guess the Madden-Julian is the only one that we don't need filtering. Okay.
Ya no vamos a tener almuerzo, comida. Nobody eats.
Esto como. Okay, can you hear me well? Okay, that's great. So let me introduce myself. I'm Christian. I'm a researcher at the Institute for Atmospheric Science and Climate Change. I have been working with tropical cyclones for 15 years, and for the last 5 years, I have been working with mesoscale convective systems too. So I have kind of experience working with this kind of phenomena. So today I'm talking about the first master's thesis that I supervised. If you're interested in look at this thesis, you can scan the QR code and read about that thesis, but unfortunately it's in Spanish. I'm sorry for that. And so I will focus on the North American region. And this region is affected by tropical cyclones, North American monsoon, mesoscale convective systems, lightning activity, prolonged droughts, heat waves, and wildfires. And if we talk about tropical cyclones, they can contribute up to 30% of the seasonal precipitation. And of course, they can alleviate some prolonged droughts over this region. And we have also other types of tropical cyclone tracks that are also important for the tropical Pacific, but most of the people think that tropical cyclones only produce extreme precipitation, but that's not right because they can also produce moisture divergence and subsidence. So they can absorb humidity and they can drive the surrounding regions because a tropical cyclone can produce heavy rainfall, of course, but can also induce subsidence and moisture divergence, which inhibit precipitation in the surroundings. So the air converges at the center of the tropical cyclone, then the air ascends and diverges at upper levels, and then they cause subsidence and moisture divergence. So if you're asking what kind of tropical cyclone tracks can do this kind of effect, they usually tend to form near to Mexico, but they don't make landfall over the country. So they can drive the surrounding regions here, and they can even make prolonged droughts worse. So they can also inhibit precipitation if you don't about it. And the North American monsoon is very active during the July and August. Of course, this kind of phenomenon occurs from June to September, but the peak activity, you can find it in July and August. So the North American monsoon is the key word for this workshop. So this North American monsoon depends on the moisture provided by the Pacific, of course, at near surface levels. And at these levels, the tropical Pacific is the important source of humidity. But this talk is about mesoscale convective systems. So if you're wondering how this is connected, most of the mesoscale convective systems occurred during July and August. And let me explain that later. First, I would like to explain what is a mesoscale convective system. That is a region where several thunderstorms have merged to create continuous area convective instability, where a cloud with a horizontal extent greater than 100 kilometers exists. That's the main threshold to consider that a thunderstorm is a mesoscale convective system. And they can induce intense winds, severe turbulence, hailstorms, tornadoes, floods, and lightning activity. The mesoscale convective systems are very popular, and they also occur over the tropics. They can contribute up to 50% of the annual precipitation, which is a lot of precipitation, if you're wondering what that means. And they can also vary in size and intensity through the time. So they usually last around 12 hours, for example, or until 1 day. We have had here in Mexico mesoscale convective systems that can last 24 hours, for example, but that are very intense, of course. And look at this region. Also, the mesoscale convective systems are important for the northwestern Mexico. So which types of mesoscale convective systems are in around the world? What are the types? So in generally, we have squall lines that are very popular in the USA, for example, bow echoes, and mesoscale convecting complexes. So this is a typical schematic of the mesoscale convective systems. You have here mature cells, oral cells. You have ascending motion, descending motion, and you have in this part heavy stratiform rainfall, and in this part you can have cuneiform rainfall, which can cause extreme precipitation events. So most of the people think that mesoscale convective systems don't affect Mexico, for example, but that's not true. We have a lot of mesoscale convective systems through the year. And this one I'm presenting here right now is a mesoscale convective system that occurred in April 2020. Do you remember that year? This is about the pandemic, so I was watching the satellite imagery all the time, so I had plenty of time to look at them. So you can see here that this mesoscale convective system was very strong. The colors represent the cloud top temperature, and the white points represent the lightning activity. So you can see here that there is a lot of lightning activity over Veracruz, my state, my favorite state, by the way, but that's another story. And you can see also here that over the Yucatan Peninsula occur other mesoscale convective systems. So you can have two systems at the same time, but in different places. If they're located very near, they can eat each other, but in the good sense. So in this thesis that is in process, we're studying how the mesoscale convective systems are varying across the different seasons. And we use the GPM data to track them. And you can see here that during spring and summer, we have a lot of mesoscale convective systems. During the spring, you can see it located mainly over the south of Mexico. But in the summer, you have a lot of regions that are affected by the mesoscale convective systems. And look at the northwestern Mexico. So there are plenty of activity during the summer months. And they also can cause extreme precipitation events. For example, look at the northwestern Mexico. You can find that they can produce up to 3 days of extreme precipitation events, and they represent up to 60% of the total annual number of extreme precipitation events, which is a lot of. If you can think in this region, they are affected again by tropical cyclones, mesoscale convective systems, and easter waves, perhaps. But the mesoscale convective systems can be one of the mainly phenomena that produce extreme precipitation. So going back to the NAN region, this is a common day in July 6, 2021. I'm sorry, I presented a lot of satellite imagery during the pandemics, but I didn't have, how do you say that? I have a lot of time to spend looking at the satellite imagery and just having fun. So you can see here that we have a lot of active convection. So when you look at the infrared satellite image, you can see there are very deep convection here. So we have monsters here that represents mesoscale convective systems. So the theses that I'm presenting here today are about how important are the mesoscale convective systems for producing rainfall over the northwestern Mexico. So you can see here that they produce up to 30% of the seasonal rainfall. So we're considered here only the months from June to September, when the North American monsoon is very active. Thank you. So this is great result from this thesis, because you can see that the mesoscale convective systems can contribute mainly over the Sonora and Sinaloa states precipitation, and over Nayarit and Jalisco. So who is from Nayarit? I remember that. 1 peso say Nayarit. So you got a lot of rainfall from mesoscale convective systems. And also, this is Sinaloa. where you can find the best shrimps in the country. For me, it's the best place. And also the chapitos, but that's another story. So this talk is also about inverted troughs. And this is a very uncommon word for everyone. So if you're wondering what is an inverted trough, an inverted trough is a trough in the pressure contours that has different orientation with respect to the primary low pressure center than the conventional trough. So conventional trough, the lowest pressure goes here, but in the inverted trough, you can see that orientation is different, right? So the inverted troughs located over the north of Mexico can be found at 200 millibars, that is around 12 kilometers, and their signal propagates downwards, reaching the middle levels, for example. It was discovered that the area of significant storm development is on the leading edge on western flank of the inverted trough. So some meteorological phenomena can origin or produce these inverted troughs that are the tropical upper tropospheric troughs and the Rossby wave breaking. So you can see here that the most active levels for the inverted troughs are 200 millibars, but you can see some signal until the mid levels. And Rossby wave breaking can originate inverted troughs because this is a normal Rossby wave. When you have this Rossby wave breaking, you can see here that the cyclone is separate from the mean flow. So they can origin the inverted troughs that I just talked about. And the tropical upper tropospheric trough, are you familiar with that concept? Raise your hand. Okay, so not so many people know this concept. For me, it's kind of new. I mean, it's becoming more popular because they are related to the tropical cyclone formation. So a tropical upper tropospheric trough is an upper atmospheric trough that enhances convection in the tropics. So it's a semi-permanent summertime feature of the North Atlantic, South Atlantic, North Pacific, and South Pacific. And a thought provides mechanisms that can suppress or support tropical cyclone formation, and it's a tree feature, and the heat or greatest vorticity and heat of the air is the coldest relative to the areas around it are not the same. You can see here in this picture that the greatest vorticity is located around here in 200 millibars, but the coldest temperatures are located below of this maximum in vorticity. So the vorticity maximum is located at 200 millibars, and the cold temperature maximum is it's about like 300 millibars. So they can also enhance tropical cyclone formation, but it's northwards of the center on the top. And southwards of the center on the turn, tropical cyclone formation can be inhibited. Why is the question? Because the thought can induce high wind shear, and on this side, on the northwards, tropical cyclone can get the favorable conditions to form. So this is very important for predicting where a tropical cyclone formation can occur. And I think I don't have too much time to go in deep. So the thought can influence the tropical cyclone formation also through divergence a lot and force the ascending. So you can get a lot of tropical cyclones here where the divergence is located, but in upper levels, of course. Here you can see the monthly climatology of thoughts. Here, the thoughts are more active during July and August. Remember that because it's very important. And they affect Mexico mainly over these months, sorry. And a thought also can enhance deep convection on the eastern edge of the thought, and over the center, it can inhibit precipitation. You can see that the stratiform convection can occur, but the convection is deeper on this side. So that's very important to see where a mesoscale convective system can occur. And I love this paper from Lammerts et al. 2016. They studied inverted troughs, and I stole that image from that paper. So you can see here that they put all the intense convection around the inverted trough. So the intense convection, for example, mesoscale convective systems can occur over this edge or the thought or the inverted trough, sorry, and also can occur on this side. And this is very important because if you're trying to match mesoscale convective systems with inverted troughs, so we need to first establish how they are connected, right? How they are interacting. So the first step was to track the inverted troughs. We use the track technique provided by Hodgetts. We use relative vorticity threshold at 200 millibars, and we use this threshold. And also, in this thesis, we suppose that all the systems that last more than 2 days and travel westward, at least 10 degrees can be considered as a inverted throw. Can you put it play? ¿Pueden ponerle play, por favor? Para que se vea la animación. And in this animation, you can see positive relative vorticity that is here. Remember, this is 200 millibars. And you can see also wind vectors. So this inverted throw is traveling westwards, and you can see a lot of positive relative vorticity. So we track all these systems at this level, 200 millibars, to get like a climatology and how the inverted throats behave over this region, over the NAM region. That was the first step. And the crucial step was to define how the inverted throat interact with the mesoscale convective system. So first, we define a radius of influence of the inverted throat. So we just try with the 4-degree radius. So you can see here in this animation that here is the center defined by the track technique that I talked in the previous slide. So you can see here that this inverted throw is traveling westwards, and then you can see that inside of the radius of influence, some mesoscale convective systems can occur. Can you put it again, please? Hopefully, puedes ponerle play. Okay, you can see here and around this region, one mesoscale convective system is occurring. Here is one, and it's another one. As you can see here, we also assume that the size of the mesoscale convective system that overlap with the radius of influence of the inverted throw, they are interacting if both areas or both radius overlap at some point. So we assume that the inverted throw is origin or causing the formation of the mesoscale convective system. So that was very difficult to get, by the way, because not all the mesoscale convective systems interact with the inverted throats. In fact, only 23% of all the mesoscale convective systems that we got during this period interact with inverted throats. So we check if our tracking and our analysis was okay. So we compared our results with a paper from Lammerts et al. 2016, and we got almost the same days with inverted throats from with Lammerts and with our study. And we also found that most of the interactions occur mainly over July and August. Sorry, these two, the table and the figure are in Spanish. Sorry for that. But the mainly July and August are very active in terms of the inverted throws. Do you remember that the thoughts are very active during these months? So the interactions with the mesoscale convective systems are more frequent during these months. And we also find the inverted throats that interact with the mesoscale convective systems produce more precipitation. The mesoscale convective systems produce intense precipitation rates. You can see here more precipitation events when compared to the mesoscale convective systems that don't interact with inverted throats. And this was a very interesting result because we didn't expect that the mesoscale convective systems produce intense precipitation rates when compared with the others that didn't interact. So we also find a signal at middle levels where the mesoscale convective systems can transport humidity outwards and until the desert of Arizona, part of Arizona, when compared to the mesoscale convective systems that do not interact. So the interaction between the inverted throats and the mesoscale convective systems are very important for defining if the North American monsoon season is going to be active or is going to be intense. And finally, I really love this result from Lammers et al. Because they analyze also the inverted throw activity and they compare different periods on inverted throw activity. So in this figure, you can see that the changes are statistical significant. So they say that the inverted throws are going to be more active here southwards, mainly located over the Baja Peninsula and the Sinaloa region. And it's hypothesized in this paper that this is due to strengthening on the anticyclone that is located here. So that's very interesting because if under climate change conditions, the anticyclone strengthens, all the inverted throats are going to suffer a displacement southwards. So perhaps, I don't know, I'm not sure, it's just an idea. You can get more precipitation events over this region. And you can get dry conditions over this region. So I don't know, that's a question for research, future research. So it's 1:20 p.m., so I have 10 minutes for the conclusions. Mesoscale convective systems contribute up to 30% of the seasonal rainfall from June to September over the NAM region. Mesoscale convective systems can produce up to 3 days of extreme precipitation over the NAM region, which represents around 60% of the total annual extreme precipitation events. Only like around 23% of the mesoscale convective systems interact with inverted throats, and the rainfall rate is higher than those ones that do not interact. In this thesis, Cerón Hernandez does not find any statistical significance in the Cape, for example. Equivalent potential temperature are the middle levels. Of the mesoscale convective systems that interact when inverted throats versus those ones that do not interact. I'm not showing these results, but it was very funny, kind of funny when you're expected to get some interesting results and you get nothing because we we compare the Cape, the vertical wind shear using different levels, for example, just in the middle levels and then upper levels. And then we analyzed the equivalent potential temperature. We didn't get any statistical significant differences between the mesoscale convective systems that interact compared with the mesoscale convective systems that do not interact. So we only saw that the vertical velocity, we have a small signal of the mesoscale convective systems that interact with inverted throats with those that do not interact, only in the vertical velocity. So it was kind of strange to see that because we expected that the other environmental factors can contribute to modulate these interactions, but we didn't get any interesting results. So research questions. It seems that the inverted troughs mainly interact with mesoscale convective systems through vertical velocity, for example, enhancing convection. Which other variables can be used to explore this interaction? I mean, it could be, I don't know, static energy, perhaps. I don't know, it's just an idea to explore. Could the inverted troughs and mesoscale convective systems interaction change under climate change conditions? As I told you previously, the anticyclone system is strengthening. So the location of the inverted trough activity is located southwards. So one question is how this interaction between inverted troughs and mesoscale convective systems are going to change under climate change conditions. And in a future climate, could mesoscale convective systems that interact with inverted troughs produce more extreme precipitation events? I don't know. That's a question for research. So you can reach me out by email or by Twitter. I'm happy to take any questions, but please just easy questions. Thank you.
So, thank you very excellent talk, very interesting. I'm wondering about how this interaction MCS IVs, what is happening? Is it that why would the presence of this low in the upper troposphere intensify the convective activity in the MCSs? Is it because these are essentially cold air vortices or something like that?
Slides. I think I skipped the one I come to my mind. Okay, I think it's this one. So that's a great question. Thank you so much. So I think that the main physical mechanism is this one. I mean, you can have the inverted trough. So you can see here that at the one edge of the inverted trough is producing, is enhancing convection. So it's through the vertical velocity, as I said. But for me, it's surprising that the other environmental variables are not changing under this inverted trough. So I think we need to analyze more sophisticated variables that can integrate all the vertical movement, for example. But I think this is the main physical mechanism that some parts of the inverted trough can enhance convection and other are inhibit the convection. So I think that's the main mechanism that we proposed in this thesis. But of course, we need to analyze other variables to make sure that it's only through like a dynamical aspect.
If I could just say something real quick. I think it's Finch and Dick
Yes.
Johnson. And I think what their argument was, at least this is for like Sonora, the higher SMO farther, what they were arguing was that the upper level troughs, TUTs, induce more wind shear in a certain way that it allows for the growing and propagation of the MCS. And they were debating other earlier papers you probably read too that said, no, well, it's dynamical effects or things like, changes by adiabatic lifting, making it more unstable. And they argued that it was basically the trough interacting with the Sierra Madre, and that was kind of the perfect combination for the MCSs to grow. But I think it's Finch and Johnson.
Yes, it's here.
Okay.
Finch and Johnson.
Really nice talk. I think my question related to TOTS and the MCSs is because the TOTS are synoptic scale systems, so they're really large. So did you observe any difference in the lifetime or MCSs? So maybe it's not changing a lot the MCS itself, but maybe it's altering like the entire environment that they are embedded, maybe making it more favorable or less favorable.
Yeah, great question. Thank you so much. No, we didn't find any relationship in terms of the size, for example, or the lifetime. You mean that? So we find that just the mesoscale convective systems that interact just produce more precipitation, and they have a well-defined circulation in terms of the ascending motion and descending motion, but just that we explore if the mesoscale convective system lifetime can change just comparing this kind of mesoscale convective systems. I mean, those ones that interact versus those ones that do not interact. But we didn't find any interesting results. But yeah, we checked that, of course. Thank you.
Thank you. Doctor, my question is about the methodology for the tracking of the MSC. I think your students use ATRAX methodology or they use another one?
Yes, I didn't mention that because of the time. There is a lot of theory and algorithms that I didn't explain in deep. But here you can see that we used this technique that is from Juan et al. 2018, and they use satellite imagery. And you can use any kind of data sets, for example, clouds, and the other one is GPM. You can use any data set of satellite imagery. So they used this method. They defined some pixels that meet the criteria. In this case, we use the criteria that the brightness temperature is less than 208, I think, Celsius degrees. Can you put it again, please? So yes, like a minus 65 Celsius degrees. And they should have a size of the deep convection of at least 3,000 kilometers. So you can, of course, vary these thresholds to define what a mesoscale convective system is, but we read a lot of papers about deep convection and mesoscale convective systems, and most of the papers say that these thresholds are the more common.
Thank you.
Thank you so much, Christian, for the very nice talk. I was just wondering, some of your composites, for instance, the specific humidity with or without an inverted trough, those composites reminded me a little bit of similar composites related to the occurrence of a Gulf surge event. And so I was wondering, is there a connection? Have you looked into it? Is it, yeah.
Yeah, thank you so much. That's one of the aspects that my student explored too, but we didn't find any relationship between the occurrence of it's called cold surges, right? So we only, so that sometimes you can have an mesoscale convective systems that travels northwards and is affecting, for example, Sonora, but other times you can have a cold surge without having a mesoscale convective system. So very difficult patterns, very difficult conditions to analyze. But I can tell you that, yes, some of the cold surges are linked to the mesoscale convective activity, mesoscale convective system activity, but not all of them. So some of the cold surges are only produced by like a strong winds that travels northwards.
Thank you, Christian. I was wondering if the lack of correlations with CAPE and things like that, you're using reanalysis, right? And would that, I mean, be deleterious to that because probably reanalysis is not capturing, you know, very localized instabilities. And also related to that, you mentioned me at least that you have this criteria with Galveston. I mean, you have other means of getting the other parameters to correlate. So I wonder what comments on that.
Thank you so much for bringing out this topic. It's very interesting for me. Yeah, we didn't analyze the Galvez-Davison index. That's an excellent question. We only use CAPE, and of course, CAPE is underestimated in reanalysis, of course. It's better to use the radiosonde data, but as you know, there are not too many radiosonde data per day. So it's very difficult to get a radiosonde when a tropical system can occur. I mean, in specific days when the specific mesoscale convective system is affecting the region where you're launching the zone. So yeah, it's better to use observations, of course. But I can tell you that perhaps the Galvez-Davison can be explored and provide more information about these instabilities, for example. And other question that I have is the use of other severe weather indexes, for example, total totals or K-index, sorry, perhaps. We didn't explore that part, but that's a very interesting question. Thank you.
I guess, what time is it now? Oh, 1:35. Okay. So we'll go to lunch and back at 3.